Now we'll learn how to calculate land surface temperature from the thermal band of Landsat 8 satellite images. So for this we need Landsat 10, band 10 of Landsat 8 and band 4 and 5 of Landsat 8 for calculating the NDVI. So these bands should be cropped for the study area to get the actual minimum and maximum value for NDVI for the given area. Otherwise, it will provide a maximum value of 1 and minimum value of -1. So, before starting the calculation of land surface temperature, we have to add both the bands from the given satellite image dataset, and here only band 10 is used for will be used for calculating land surface temperature. And for calculating land surface temperature, first we have to convert this band 10 into top of the atmosphere from using the raster calculator function, which is available within the processing toolbox. So within this raster calculator, the first we have to put this formula of converting dn value to TOA, that is ml into qcal plus al. Ml is the multiplicative factor and al is the additive factor for converting this dn to top of the atmosphere, and this ml and al value is available in the metadata file, and this qcal is the actual pixel value. So first we have to identify the multiplicative factor value from metadata file available within this satellite imagery, which is radiance multiband for 10. The value is 3.3420 e minus 04. That means the actual value will be 0.000333420. So if we put this value into raster calculator console area, and after that we have to add multiply it with the actual pixel value, which is band 10. So if we double click on this, and it will be added. So we have to keep this within a bracket, and then we have to put the additive symbol and its corresponding value that is also available within this metadata, and the value is 0.1. So we have to put the value 0.1 to convert it into TOA. So after putting these algorithm values, then we have to specify the pixel size, and then we have to specify the output extent. In this case we are given the output extent as band 10 because we want the analysis for this area, and then we have to specify the projection system, and then we can put output folder location. So here I am putting TOA for the cropped image. So then click on run. It will execute the program, the algorithm that we have written, and it is already added into this layer panel as well as in the canvas. After that we have to convert this TOA value to brightness temperature following this formula, that is K2, which is a constant, divided by natural log of K1, which is also a constant, then L, that is TOA value, plus 1 minus 273.15. This 273.15 is actually used for converting the Kelvin value to Celsius value. So again we are using a raster calculator for putting the value of K2, that is 1321.0789, then natural log of, that is ln function, that is available within this raster calculator. Then we are putting the k1 ln of k1 value, that is also available within this metadata, that is 774.895. It may change according to the changing of satellite image, and then we have to put a plus divided by top of the atmosphere data, then plus 1 to complete this bracket, which is also a constant value. After that we can we have to specify the pixel size, then processing extent, then output projection, and then output file. Actually we are separately calculating the brightness temperature in Kelvin, then we will calculate it for degree Celsius, which can also be calculated simultaneously within a single algorithm. So after that, we are will convert this into degree Celsius from Kelvin. So the formula will be B10 BT, that is brightness temperature, divided by 273.15. So 273.15 is subtracted from the value to convert it into Celsius. So the similar process we have to follow to specify the pixel size, the processing extent, and the projection system, and then we can specify the output location. So giving the name BT underscore Celsius C. So after this calculation, now we have to calculate emissivity, and for calculation of the emissivity, first we have to calculate the NDVI. So NDVI formula for this, the band 4 and 5 will be used, and the NDVI will be calculated based on this raster calculator, so which I have already explained in a different video. So the formula will be band 5 minus band 4 divided by band 5 plus band 4. After writing this algorithm, similarly we have to specify the pixel size, extent, and projection system, and then output file. After the calculation of NDVI, then we have to calculate the proportion of vegetation, which will be calculated from the NDVI using the same raster calculator formula. So the formula for calculating proportion of vegetation is square root of actual NDVI value. That means we have to. So for calculation of proportion of vegetation, we have to put NDVI minus minimum NDVI value. The minimum NDVI value can be obtained from the layer panel minimum value of the NDVI, as the minimum value is minus 0.14363. That means it will be a plus value. So NDVI plus minus 0.14636 divided by maximum NDVI value minus minimum NDVI value. So after giving this maximum and minimum NDVI value, we can calculate the algorithm will be fulfilled, and then we can go for further processing. So why I have taken only the crop image, because to calculate this maximum or minimum NDVI value. Otherwise, if I take the whole image, then it will provide a minimum value of -1 and maximum value of +1. So after that, we have to specify the pixel size, as earlier we have specified. Then the processing extent, as I am giving processing extent for band 10, and then we have to specify the projection system, then output file. So I am saving this file as pv underscore crop, as I am calculating the proportion of vegetation for the cropped image. After clicking on run, it will complete the processing and it will be added in the layer panel as well as in the map canvas automatically. So after that, we have to calculate the emissivity and the formula is 0.004, which is the constant, multiplied by proportion of vegetation plus 0.986, which is also a constant. So similarly, using the raster calculator, we can put this value. It is better to write the value instead of pasting the value into this console, because there may be some error in the formula. So after putting the value of multiplicative constant, then proportion of vegetation, then plus additive constant, which is 0.986, which is common for each of the satellite sensors. So after that, I have to specify the pixel size, which is 30, as the pixel size for Landsat image is 30 meter. Then specify the extent, projection, and output file. So after that, it will be the proportion emissivity of this area will be calculated. Pixel wise emissivity will be calculated, which will be further used for calculating the final land surface temperature. So it is calculated, and then the last step of calculating land surface temperature is to convert this brightness temperature into land surface temperature after incorporating emissivity. So the formula is brightness temperature divided by 1 plus 0.00115, which is a constant, into brightness temperature, it should be at Celsius, in the Celsius degree, divided by 1.4388, which is also a constant, then it will be multiplied by the natural log of emissivity, which is calculated. So after that, after putting this algorithm, now we have to specify the cell size again, the processing extent, the projection system, and the output file. The list will be calculated in degrees Celsius, and after the running of this algorithm, it will be added into this layer panel as well as in the map canvas. So it is already added. The value is ranging between 24.91 to 35.52. So if you want to change the color of this image, then we have to go to this properties, symbology, single band pseudo color, then we can change the color as per our requirement. So after changing this color, now we can uh, go for final apply. Then this is the Landsat temperature map of Asansol Municipal Corporation area calculated